In this week's video, we will be discussing calorimetry. For our first problem, a piece of titanium metal with a mass of 20.8 grams is heated to 99.5 degrees C, and then it is dropped into 75 grams of water at 21.7 degrees C. The final temperature is 24.3 degrees C. What is the specific heat capacity of titanium? It is important in this problem to itemize which species are gaining and which ones are losing. So the first thing that we must do is itemize which species those are. In this problem, our titanium is going to be our loser. So we need to write negative Q of our losing species, which is going to be our titanium. That is going to be equal to the Q of our gainer, which is going to be the water. How do we know this? Its temperature is going up. So now that we have our species itemized and we know that our 75 degrees of water is going to gain, we need to write two Q equations. The first one is going to be negative MC of our titanium times its delta T, and set that equal to our MC of our water times its delta T. So what variable do we need? Well, we're trying to solve for our specific heat capacity of titanium. So now we have our C of our titanium is going to be equal to everything on our right side, all of our water variables. That is our mass, our specific heat of water, and its delta T. We will put that over the negative mass of our titanium and its delta T. Make sure to keep a track of that negative from the loser side. So now we can look to see if we have all of the variables for this equation. First off, we need our mass of our water, and that is 75 grams. Even though it's not listed, we now need to put in our C for our H2O. This is a known value of 4.184 joules per gram degrees C. This is a value that you are expected to know. Now we need to go look at the temperature change of our water. Our final is 24.3. Our initial is 21.7. So we need to put in our 24.3 degrees first minus our 21.7 degrees C second. Now for our denominator, we must be concerned about our negative. So our mass of our titanium is 20.8, but let's put the negative out front. Inside our first parentheses, we'll put 20.8 grams of titanium. And finally, we need to worry about its temperature change. The final temperature is the same as that of the water. Our initial is 99.5. So in our bottom, we're going to have 24.3 degrees C minus 99.5 degrees C as well. Let's look at our unit cancellation. Our Celsius will cancel on the top. Our grams of water and grams will cancel. But now we're left with joules, grams of titanium over degrees C, which is a good unit for our specific heat capacities. If we put all of this information into the calculator, you will get a value of 0.522 joules per gram degrees C for our titanium. It's important to know which variable you are solving for, but more importantly, which species gains and loses. In this case, the loser was a titanium, the gainer was our water. For our second problem today, an ice cube of mass 9.0 grams is added to 120 grams of hot water at 90.0 degrees C. If our delta H of fusion is 6.0 kilojoules per mole, what is the final temperature after mixing? We must do this problem in two distinct parts. Those two parts are going to be handled differently. The first part is going to be the melting of the ice cube. How much energy is it going to take to melt the 9 grams of ice? And that energy must be supplied from the hot water. We will call this part the melting. Our second part then is going to be mixing two different quantities of water. One that is still warm, and now the second that is going to be from our 0 degrees C, from our melted ice. We will handle that part secondly. So let us start with part one. The first thing we need to do is take our 9 grams of our ice, or H2O, and we need to turn that into moles. The reason we do this is that the unit is kilojoules per mole. We cannot do this with grams. So we're going to say that 1 mole is over 18.016 grams. And now we can multiply that value times our heat of fusion. So we're going to put 6.0 kilojoules over 1 mole. This value would be supplied to you. If we do this math, you'll get a value of 3.00 kilojoules. This is the amount of energy that the ice needs to absorb to melt. So now what we need to do is look at how much energy the water has to release to do this. That is done by using Q equals mc delta T. Our change in temperature is ultimately going to be what we solve for. Now look at our energy. It's positive. So this means that our water must be negative in order to accomplish this. Doing a little unit conversion, we will get 3,000 joules. So now our M is going to be 120 grams. Our specific heat of water, once again, is 4.184 joules divided by grams degrees C. And our final temperature is going to be left as our unknown variable. And our initial temperature is 90 degrees C. For this problem, we are going to solve for T final. We will leave the minus 3,000 joules alone on the left side. But if we multiply our 120 grams times 4.184, we get a value of 502.1 T final minus, if we go ahead and multiply 120 times 4.184 times a minus 90, we get 45,190 joules. Now we must collect all the joules on the left side. This is done by adding 45,190. And you'll get a value of 42,190 joules equals 502.1 T final. To isolate our T final, we will divide both sides by our 502.1. If this value is put into a calculator, you will get your temperature final of 84.02 degrees C. This isn't our final temperature, but this is the temperature that the hot water has now reduced to after losing energy to melt the ice. This will become our initial temperature in the second part of our problem. So now we can go to part two of our problem. But now we have to figure out our gainers and our losers. So just like the first problem we had today, we'll have minus Q of our loser equaling Q of our gainer. The loser in this case is going to be our hot water. Our gainer is going to be our now created cold water from our ice. So now we will get negative mc delta T equals mc delta T. The good part about this problem is that we have the same material, both of it being water. This allows us to cancel out our specific heats. So now if we expand out our change in temperatures, you will get negative Mi times T final minus Ti. The I in this case is being used as the initial temperature of the hot water. This is equal to MO, the mass of our cold water, times the final minus the initial, TO, for our other species. If we expand this all out, you will get negative Mi times our temperature final plus Mi times Ti. So again, these are the species of our hot water. This is equal to our MO times temperature final minus MOTO. These are the values associated with our cold water created from the ice. Now we want to collect our terms together. Notice that we need to get our finals on the same side. So we will bring the MITF to the other side while we do the same thing with our initials. This will get us Mi times Ti plus Mo times To, setting this equal to MITF plus MO times TF. Notice that we can isolate out our TF values on the right side. So what we can do is finally determine our temperature final. TF is going to be equal to everything on the left side of our previous equation. That's MITI plus MOTO. And now we can divide that by the sum of our two masses, Mi plus Mo. Now we must determine what species are our variables. Our Mi is going to be our hot water. So that's 120 grams of our hot water. Now our hot water temperature is our previous final temperature from part 1. So this means that our initial temperature of the hot water is going to be 84.02 degrees C. We're now going to add that to the mass of our ice, so that is 9.0 grams. And our current initial temperature of that cold water is 0 degrees C. The good part about this term is that it will cancel to 0. 9 times 0 is 0. So if we go and sum the two masses on the bottom, that is 120 grams plus 9 grams, we'll be able to put this in the calculator. If we solve for our T final, you will see that we get a value of 78.2 degrees C. Notice that after part 2, our temperature has reduced by another almost 6 degrees due to the cold water mixing with the hot water. In the two problems today, you have had to itemize which species gain or lose, uses of MC delta T, but more specifically, good variable identification. Good luck.